And our next speaker is Tang from the University of California in Santa Barbara, who will speak on the data-driven discovery of linear dynamical systems over graphs via dynamical sampling.
Okay, thanks for the introduction. So first of all, I would like to thank the organizers for such a wonderful session and the invitation. Today, I will present the data-driven discovery of linear dynamic systems over graphs via dynamic sampling. So this talk is more focused on the signal processing perspective of dynamic sampling. And the research is partially supported by funding from NSF and the Regions Fellowship from UC Santa Barbara, and as well as the travel grant sponsored by Siemens Foundation. In particular, I will present some preliminary progress on two sets of problems. The first one is about the randomized dynamic sampling of banner-limited graph signals. This is based on the joint collaboration with Nongshu Huang and Diana Needle from UCLA during the pandemic. The second set of problem is about recovery of the evolution operators via dynamic sampling techniques. So I will mainly present the work with my previous student, Jiahui Chen, who is now at Georgia Tech. And if time permitted, I also want to discuss some ongoing work with Mauro Maggiani and Chris Kimmerer from Johns Hopkins University. Okay, so let us start with the motivation. So why we are interested in graph signals? This is motivated by their presence in various applications. So below I show a few examples. And in the first example, we have a social network where the black dots here represent users and the edges represent friendship among them. So if we have any information defined on the social network is a graph signal. The second example is the sensor networks that are often used to sense some physical field like temperature. So in this graph, the nodes represent sensors and the edges represent the communications between them. So the other examples include the traffic data defined on the road network. Here is the Minnesota network where data defined on geometric point clouds. And here is a cute plot of Stanford bunny. Motivated by the large demand for processing the data on graphs, actually, the graph signal processing has received a lot of attention in recent years, where a fundamental problem is the sampling and the reconstruction of graph signals. So what is this problem about? And below here, I show a very simple example. So consider we have a community graph, and we have so this is a graph with 256 nodes. And we have some unknown signal defined on this graph, but we are only able to have partial observation. So the question is how to choose the locations we observe such that we can recover the missing information on other nodes in a good way. And clearly, if we don't have any constraints on the signals of interest, and this problem doesn't have exact solution, and find the best approximation to the signals may be an LP hard problem. But unfortunately, many real-world signals display low-dimensional features, and one of them is smoothness. So once we have this kind of low-dimensional features, then the exact recovery and the exact and accurate recovery from the partial observation will become possible. So after we specify a signal model, then the next question is to ask like how many samples and where to sample. So this is a sample so we want to develop sampling theorems. And also because this is a graph, so the natural question arises is that how to leverage the structure of graph to smart sampling. So these are the questions we want to address. So back to the signal model. So in classical signal processing, like a fundamental class of smooth signals, for example, we often use in applications is a banner-limited signal. Then the question is that how to define the smooth signal over the graph. And recall that in the banner-limited signal are defined while the Fourier transform. So we may want to generalize Fourier analysis to graphs to define the smooth signals. So here is the idea. So in this slide, I introduced some useful preliminaries. So now let us keep the life simple. We consider a simple and directed graph with n nodes and with set of edges, and we have a weighted and adjacent matrix. And this weighted matrix actually encode the similarities among the nodes. And then we can calculate the matrix D, which is a diagonal degree matrix. So which the entry here, DII, is the total degree of the node I in this graph. And after this matrix are defined, and then we can introduce the graph Laplacian matrix. You may see variants of the Laplacians depending on the specific applications. And here are two of them. But in any way, this graph Laplacian is a generalization of Laplacian operator of the real line. And in this case, it is always like a positive semi-definite and a symmetric. So we do have orthonormal eigenvectors of L serving as a generalization of the Fourier matrix. And then we have like n eigenvalues of L, and we can define the semi-notions of Fourier coefficients of the graph. So here it is. And then X is k-balanced if we say this X actually lies in the spine of the first k eigenvectors of the graph Laplacian L. So this is the definition. Then you may ask, is this a reasonable model for real-world applications? And in the following, I'm going to show like two nice examples. And these two examples are taken from a paper by Chen, Wama, and Tang and Kovacevic back to 2016. And the first example is a real data set about the wind speed across Minnesota. And so, on the left-hand side, it is the plot of the singular values in the spatial domain with their intensities indicated by colors. And on the right-hand side is a plot in the frequency domain. So you can see that this signal is approximately unlimited. Another example is the temperature readings across the United States. And it is also can be viewed as a approximated unlimited graph signals over this sensor network graph. And motivated by these applications, and there's a lot of like research interest in developing the sampling theorems for band-limited graph signals. And the problem statement is like how to like find a set of V naught, a subset of V that can yield robust recovery of band-limited signals provided noisy samples. And this problem can be studied for both finite graphs and infinite graphs. And of course, and one can generalize the Shannon sampling theorem or to the graph setting. And especially in the finite dimensional setting, it is intuitively to say that if this signal space has a degree of freedom k, so one should expect that we need to sample at least k nodes. And this is the case, and such like k nodes always exist. But really the hard question is how to find the best one that can ensure the robust reconstruction. So in the worst case scenario, it's like NP hard problem. And in particular, how to leverage the structural graph to do smart sampling. So these are two algorithm challenges people want to tackle in the sampling questions. There are many works trying to solve these two problems. And depending on the like sampling theorems, it could be categorized to the determined sampling and random sampling. So in the determined sampling, we want to say, yeah, we can give us a determined reconstruction, and one can do it do the exact recovery 100% sure. But in the random sampling, we actually drop these determinacies. We look for the successful recovery with high probability. So in this talk, I'm going to follow more work on the random sampling, in particular the work by Vander Ginst back to 2018, where they use the idea from computer sensing more precisely the variable density sampling theorems. I will give more details later. So all of these works mentioned here actually assume there's no time evolution for these graph signals, and they are all static. And this will become tremendous limitation in scenarios when the signals are actually evolving over time. And here I gave like 2 examples, and you can, I mean, in many situations, we may have like time varying graph signals, and we can see the graph signals are changing continuously over time. And in the first plot, you can see this is how the temperature of the Earth changing over years. And on the second plot is how the traffic flow involved in the Phoenix city. So motivated by this application, there has been an active research line on reconstructing the time varying graph signals from space-time samples. And of course, different dynamic models have been proposed, and a different optimization approach has been proposed to solve the reconstruction problem. And but according to our best knowledge, the sampling theorem for time varying graph signals are still underexplored. And in this talk, we want to make an effort in developing sampling theorems for time varying graph signals. And we restrict our attention to linear dynamic system. Why is that? Because it is simple model which allow us to do a refined analysis. On the other hand side, the linear dynamic system actually have a lot of wide applications. So many dynamic processes are actually linear dynamic systems. For example, the random walks and heat diffusion process, and more generally like the filtering process. And also many nonlinear dynamic systems can be well approximated by linear dynamic system as a first order approximation. So this kind of perspective is used a lot in control theory when people do dynamic model decomposition. So more precisely, we are going to start with the heat diffusion process over the graph. So how to define this equation? So you may notice that here we replace the Laplacian operator with negative L, and you can use any type of Laplacian matrix here. And then we'll assume this initial signal X is K by anonymity. And this K is fixed. And of course, it can be arbitrary value between 1 and n. And this is our setting. Then we introduce the dynamic sampling problem for the graphs. So you may see this definition in Akram's talk. And here we just generalize it to the graph settings that, okay, now I have a heat diffusion process. I have an unknown initial signal X naught. So how and when the space-time samples determined by some state omega can give us like robust recovery of this X naught. So these are the problem we want to tackle. Then you may ask why space-time samples, and in Akram's talk, he also gave the motivation here. I just do a bit like revision. This goes back to Lu and Vitaly's work in 2009. So sometimes we do have restrictions and the number of spatial samples we can take at a single time instance. For example, I want to recover a signal with bandwidth 100, but we are only able to sample 10 at each single time instance. So this is definitely not enough. But in the dynamic system setting, you can do observations at multiple times. So we can use the temporal information to get the exact recovery. So this is the idea. On the other hand side, compared to the same number of spatial samples, and the space-time sampling is much cheaper, because in principle, we can use few number of sensors with more frequent acquisition. So this will save the cost of data acquisition. Okay, so what about this? So I want to give a summary of the previous work. So the majority of the Morse work has been done to do the deterministic sampling theorem, and with the sampling pattern given shown in this figure. So here I use a different notation F to say actually we assume the bandwidth is n, so we don't assume like if the bandwidth is small, and we consider the uniform the observation time instance are uniform, so it will be a discrete linear dynamic system sampled from a continuous time heat diffusion process. And so we place a set of sensors at the initial time as shown here. So this is denoted by omega 0. So we observe at this blue location. Once we fix it, and then we keep observing at each location until some time instance. So you can see it's here. And this time instance may vary for locations. And so so you can see that overall, we are going to have like coarse and coarse samples over the time. And how did we tackle the dynamic sampling problem? And so we solve it by making an elegant connection with the frame and the basis theory. So this will allow us to leverage tools in harmonic analysis to study it. And this collection is summarized in the following lemma. So this is only a finite dimensional setting. So of course, in general, it's true for infinite dimensional case. So if we say this omega 0 is nice, like we can do stable recovery, and only if the set of vectors showing here is a frame. And this set of vectors is in fact the trajectories of the joint linear dynamic system generated by this A with initial conditions starting from EI for I in omega 0. So you can see that study the frame properties of this set of vectors shares a lot of similarities with other well-known problems in harmonic analysis. And for example, consider in the infinite dimensional setting, we choose the EI to be functions in L2, and A is translation operators, and then we study whether the translate of functions will be a frame or L2, and this is closely related to the exponential frame problem considered in, for example, the Levsky's talk and as well as Osler talk. Then based on this collection, so many of the works has been done to develop theorems on the interplay between the omega 0 and as well as the operator A, such that this set of vectors is a frame or real spaces in general. So here is the incomplete list of the summary of the work, and in Akram's talk, he has already gave a very nice review, so I will not say too much for this slide. So here I want to emphasize several speakers in this session have made various contributions to this problem, such as Christensen and also Ursula and Akram, of course, and also Jose Romeo, and they recently have a nice work in the continuous dynamic sampling problem. So in this talk, I'm going to depart from the frame perspective. I'm going to shift my focus more to the relationship with the linear inverse problem, where we want to make connections and design smart strategy to choose space-time samples that can do as good as the spatial samples. Why I'm saying this? Because here, essentially, we are doing the source localization problem in the theta diffusion process. And it is well known as a kind of ear-post problem. So by making connections with inverse problem, we hopefully to make to leverage the preconditioning techniques and also the regularization techniques in the linear inverse problem to help us to solve the dynamic sampling problem in a stabilized way. So the formulation is as follows. Because in our setting, we first assume A is known. Okay, so we take different space locations at a different time denoted by omega 0 or omega t minus 1. So this is going to be a linear process. So we are going to represent any space-time sampling as a operator formulation shown here. So from inverse problem setting, we are given the noisy samples is Y and we know S, and exactly I want to recover the X naught. And here, and let me introduce some notation. This S omega is the standard sampling operator, and it's diagonal. So if the entry I is 1, if I is in this sampling set, otherwise it's 0. Now the core question we want to solve is how to make this operator as well condition. In particular, more precisely, we want to use randomized techniques. So we propose 3 different random space sampling regime that account for the various scenarios and constraints we may have in practical applications. And below, I gave a sketch of 3 regimes. And still, I'm considering graph signals. And here I represent the data in the matrix to have more space. So here we have a signal, it's 40-dimensional, defined on a graph. And this matrix of data is the time evolution data of this single graph over 20 time steps. So in regime 1, actually, I do random sampling at t to 0. So in this example, it's 2. So these colored points are the one I observe the signal. And I fix it, and I keep observing at these 2 locations in future time instance. So this is kind of randomization of the sampling pattern we considered before. However, we also introduced two new random regimes. And in the regime 2, we do random selections of locations at consecutive time. So this is to account for the fact that maybe at a different time instance, we have different, we can sample different numbers of locations. So in this example, I random select 2 for each location, for each time instance. So this is summarized here. And in regime 3, we integrate this spatial access and the temporal access together as a product set. So I do random selection from this space-time locations directly. So the regime 2 and regime 3 are different. So you can see from this in the regime 2, for each time instance, we do have samples, but it is not necessarily true in the regime 3. So in the following, I'm going to represent the space-time sampling regime with the operator formulation. So this can allow us to make connection to inverse problem. So I want to have a regular definition. So in regime 1, our sampling really rely on probability distribution, which we call P1, and is defined on Rn, actually it's not Rn, so it's defined on the N. So it's sorry, this is a typo. So it's N, and it's non-degenerate. It is non-degenerate everywhere. And at t equals 0, we draw m independent samples, omega 0, according to this probability. So the probability of that omega j equal to I is exactly given by P1I. And if we choose this omega 0, then we will let omega t equals to the omega 0 for future time instance. Then how to define the sampling operators for region 1 in this case? So we introduce an important map pi at. So this map actually mapping Rn to Rtn. So for any signal x, so this image of pi at is exactly the trajectories and this linear dynamic system. And then we define a sampling matrix. This is a block diagonal matrix, and with identical copies, actually t identical copies of the sampling matrix S10, because here we have omega t equal to omega 0 always. So that's we have the identical copy here. So this sampling matrix is just as we defined it before, it's standard sampling matrix. So after we introduce these operators, then we can represent the sampling process here as in this format. So this is going to be a inverse problem. So in regime 2, so we can do a similar thing. Here, again, I apologize, this is a typo. It should be the discrete set 1 over n, 1 to n. So here, different from regime 1, we are going to have t different probability distribution, like P1 to Pt. And so at each time instance, we draw MT independent samples according to this probability Pt, and we denote this set by omega t. Then this omega is the union of this omega t times the time instant t. So in this way, we give the space-time samples. And then we can use the similar tricks as regime 1, and we formulate the sampling process in the inverse problem setting like here. And the same for regime 3. So here I define a probability distribution, now not on n, but in the nt's for 1 to nt. So I sample I draw m independent samples from according to this probability. And again, I want to represent in this operator format. And then the question we want to solve is that, okay, so now we do have a random sampling regime. Then how many samples do we need to make these like operators well conditioned or well behaved? So in one way, they actually be affected by the sampling distributions and the graph structures and the temporal dynamics. In particular, can we actually exploit the graph structure and the temporal dynamics to help us to choose the best sampling of the distributions to make the sampling operators well behaved, but with the least amount of number of samples? So these are the questions we want to solve. So how to solve these questions? We first make connections with steady case, capital T equal to 1. And really, when T equal to 1, all regimes will be the same with a random sampling model proposed for the recovery of bandlimited graph signals, and this model was proposed by Vander Gis and his group back to 2018. Okay, so how to determine if a sampling location is important or not? And a key quantity to give a good description about this is consider the concentration of a perfect impulse at the location I. So this delta I is a Dirac mass, so it's 1 at I and 0 anywhere else. So what does this quantity mean? So this quantity is always a number between 0 and 1. So if it is 1, this means that delta I is, this means that delta I is a k bandlimited signal. If we don't sample at the location I, so this will actually decrease the recovery probability a lot. So this means I is important. On the other hand, if this quantity is 0, this means that these bandlimited signals don't have energy concentration on their load. So it's not important. We don't need to sample it. So according to this intuition, so we need to have this probability PI match whenever this quantity is matched. And then based on this intuition, we could introduce the graph coherence and showing here. So it's a ratio between this quantity over the square root of PI. And we consider worst case scenario. So it turns out that the sampling complexity required for this random regime is crucial, dependent on the square root of a square of this graph coherence. In particular, we can show that this is always bounded below by square root of k. So from here, you can see that in the optimal regime, we can use k log k samples to do the stable recovery as desired. And in particular, in this case, the inequality can be achieved. So here we can choose the probability according to the structure of the graph, and while its interplay interplay between this delta I with the Fourier basis of the graph here is a UK. And so the idea of this kind of sampling is called a variable density sampling, originally in the comprehensive. So in this talk, actually, we're going to make connections with the static case. So how do we make these connections? So we make like several k observations. The first one, we observe that if x is a bandlimited signal, and then this match pi x actually provide a stable embedding from this original signal space to the trajectories of linear dynamic systems. So we do have lower bound and upper bound. So this ft is going to be a function, increasing function of the time t here, and with a minimal value 1. So it's a stable embedding. And the second crucial observation is here. So after we do the embedding onto a linear dynamic system trajectory, actually you can view it as a bandlimited signal over an extended graph. We say it's GT with the NT nodes. And the Fourier basis for this space-time graph is shown here. So you can see that in this Fourier basis for the larger graph GT, we do see the interplay of the graph structure as well as the temporal dynamics. So this U1 to UK are the Laplacian matrix of are the eigenvectors of the Laplacian matrix, and these values lambda 1 to lambda k actually are the eigenvalues of this evolution operator A. So you can see they are really interplaying here. So in this way, we collect the space-time sampling with the static sampling. So based on this collection, we can introduce various notions of spectral coherence of order t, kt. So k representing the bandwidth and t represent the time steps we take. And so in all our regimes, you can see this spectral coherence actually describe the interplay of the space-time locations with the generalized extend graph Laplacian matrix of this GT, of the bigger graph GT. And it turns out that this spectral coherence for various regimes here and is here are also crucial in determining the sample complexity for each regime to achieve the stability. So in this theorem, we leverage the recent advancement in non-asymptotic analysis in comprehension to provide a theorem that gave a unified description for all the regimes we have. So no matter what kind of sampling distribution PGA we use in the regime, and for any delta and epsilon between 0 and 1. And the following inequality here, so later I will give a detailed explanation, holds true with high probability. As long as we do have enough samples, there is M and MT are bounded below by some number, like here is proportional to the square of the spectral coherence we defined in the previous slide. Okay, so in this embedding inequality, we do require X is in the spine of UK's K band-unity. And these two operators serving as a kind of preconditioning operators, they are like reweighting operators, and they can be done offline. Particularly, this WJ is going to be some normalization by the number of samples, and this one is related to the sampling the values of the probability we used in these regimes. And also the total samples for regime 1 actually is M times T, but here, so really the sample complexity is dependent on T times the square root of this coherence. And in the regime 2, the sum of MT for all like a time instance, and in regime 3 is M. And when T equal to 1, both of this bound will equal to 1. So this is exactly the restricted isometry property established in this reference work. So here we generalize to the space-time sampling regime. Okay, so then the question is that, and how large are these spectral coherence are, and what's the relationship among them, and what's the minimal values for them, and could you derive the optimal sampling complexity? So these are questions we want to solve, and they're all solved in the following proposition. So we do a very detailed analysis of this spectral coherence, and in particular, we derive the closed formula for the optimal sampling distributions. So here, like in 8.1 to 8.3, we derive the lower bound for the coherence as shown here. So in particular, in 8.1, we show that this bound is always achievable by writing down the optimal sampling distribution in this way. And we can show that this quantity is always bounded below by K, but it is not necessarily true that this equality can be achieved. But in regime 2 and regime 3, we actually can do more. So you can see here, we do have the lower bound, and we have the closed formula for the optimal sampling distribution. And in particular, this K can be achieved. So this says that actually in regime 2 and regime 3, we can really adapt the graph topology and temporal dynamics well, such that the K log K space-time samples can do a very good job as the same number of spatial samples. And then what's the relationship among this spectral coherence? So in the 8.4, we give the answer. So for any sampling distributions, no matter what kind of sampling distribution you use here, we actually have this inequality. So this indicated that if we want the corresponding sampling operator to be has a comparable, like say the low the conditional number, and then we would require the most number of number of space-time samples in the regime 1, and the least number of samples in the regime 2. Okay, so and next we are going to show several numerical tests to support our theoretical findings. But before that, let me make a summary. So the optimal sampling distributions really depends on the graph structure and the temporal dynamics, and which generalize the idea of variable density sampling in compressed sensing. And our bounds shows that, yeah, regime 1 so shows this equality in terms of sample complexity. And in particular, in regime 2 and regime 3, we can do really well, we can use K log K space-time samples, ensure the stable recovery with high probability. Now let us say some like specific numerical experiments. So we perform the experiments over a variety of graphs, and like community graph, Minnesota graph, Bunny graph, center graph, and also path graph here, and over the heat diffusion process. And then, so first let us consider a probability event. So here we want to say, okay, now you give me a graph, and I choose some number of space-time the space-time samples range from 0 to here is 4,000 for the path graph. This path graph has like 1,000 nodes. So we want to count the probability of the event. So given this M, we form a sampling matrix. So we want this smallest singular value of the reweighted sampling operator is greater than some threshold. So for each choice of M, we run like the experiments like 250 times. So we count the successful probability when the event is true. So here is the summary for regime 1, regime 2, and regime 3. Here, this 100 means that we are considering the bandwidth with 100. Okay, so you can see here, this red curve is optimal sampling distribution, and the blue curve is the uniform distribution, and they all like match all theoretical findings. In particular, here I want to make a remark because this plus graph is regular, so you can show analytically that in the regime 1, this uniform distribution is the optimal sampling distribution. They are the same. In regime 2 and regime 3, they are very close, and with the discrepancy controlled by the eigenvalues. So they are also very close. So that's why you don't see obvious like performance gap between the uniform and the optimal sampling distribution. But the story will change when the graph becomes less regular. So we do a test in a set of community graph, which is becoming less regular here. So this is a graph with 10 communities with equal size, and then we shrink the size of one community and increase the size of another community, and here we shrink more. So in this way, we are making this graph less regular. So in this case, you can say that it's kind of intuitive. Like in this less regular graph, the information is not mixing that well. So you would expect that to achieve the same level of stable recovery, you would require more samples in this less regular graph. So this is exactly the case when you look at the three like plots, and this orange graph would require the most number of samples, while this black curve represents this more regular graph require the least amount of samples. And this is for uniform distribution. However, if we use the optimal sampling distribution, okay, to incorporate the graph structure as well as temporal dynamics, yeah, so they basically have some identical like performance, like the gap actually shrink a lot. So this is the plots, and then we also kind of like compare how the coherence over T change over time, because this quantity give us the sense like how the average number of spatial samples we need to take. So you can see that in the regime, so this like we have several curves here. So this curve with circles are uniform distributions, and the curves with plus sign the optimal distribution. So you can see that in regime 1 here, and also as time evolves, so from 1 to 20, this curve decay very slowly. So this gave us the indication that actually this temporal correlation only brings a tiny reduction in the average number of spatial samples we use in regime 1. So this is really a challenging situation we're considering. While in the regime 2 and regime 3, when randomize the space-time locations, and then you can see we can see the curve decay kind of smoothly, and in particular in the optimal sampling distribution. So this means that the regime 2 and regime 3 can be more adaptive. Okay, so we also testing over larger graph, the Minnesota graph and the Barney graph, and for all the regimes. So here I want to like just emphasize here, like in the regime 2 and regime 3, regime 1 and regime 2, we don't see many like obvious gap between uniform distribution and the optimal distribution, but then things changed rapidly in the regime 3. So here you can see that in this regime, if I use optimal sampling distribution indicated by the red curve, I can use far few samples to achieve the stability. While in the uniform distribution, I have used a lot of more samples. So this shows the advantage of using the optimal sampling distribution. Okay, so then we also compare the dynamic sampling with the static sampling. So the comparison makes sense inside this red text box. So you can see that compare like this, we use a uniform distribution. If we want the corresponding sampling operators has like comparable, has comparable performance, And then we calculate like the average spatial samples in the dynamic sampling regime, and also the total number of spatial samples in static regime. So you can show that we actually can use far few like number of samples in the dynamic sampling, yet the same level of stable reconstruction. And particularly in Barney graph, and here basically this test failed. Like even with sample 2,000 spatial samples, it can still not provide stable recovery for the signal with bandwidth 100. But in the dynamic sampling setting, we use the dynamic information. So you can say that we use like at most 200 samples even in regime 1, we can do a good job. Okay, so I will go briefly with the reconstruction strategy. So as I mentioned, as long as we have like well-behaved, if we have a well-behaved sampling operator, so we have a lot of techniques in linear inverse problem can help us to do inflational reconstruction by using this connection. And here I mainly introduce 2 types of encoder. And the first one, standard encoder, also propose advantages the work. So here you do, here is a typo, sorry, it's a least square problem. And this is reweighting operator for stability. This is the data samples, and this is sampling operators. This is the signal of interest we want to recover. Here, this minimization is over this banding space. And so in order to solve this optimization, you need to compute the Fourier matrix UK. Sometimes if the graph is very large, so this is going to be very expensive. So people would like to use the inflation decoder, where they do a relaxation on the domain. So here they relax this domain to the whole space Rn, so we don't need a projection. But instead, we add a regularization term here. So this gamma is regularization constant, and G is a choice of filtering function. So I think it's a very interesting example here is that the standard decoder is actually a special case of efficient decoder. If you choose this function G carefully, exactly, and this regularization can be viewed as a projection to the UK. But now you don't need to actually compute the spectral decomposition of an application matrix. And here it's just like multiplication of the matrix. So in this way, you save a lot of computational cost. And here are the guarantees for both standard decoder and efficient decoder. I don't want to go much details here. The point I make here is that as long as the noise equal to 0, so we do have exact recovery because all the terms here goes away. In particular, this function here is the increase function of t. So you have t larger, then this bound will shrink. Okay, so also for efficient decoder, I also highlight the bound only involve this noise-free reconstruction. So if e equals 0, so we can make everything like exact reconstruction. And this bound will actually tell us how to choose the gamma and how to choose G to minimize the bound on the right-hand side. So I will not go many details in this theorem. And we perform a lot of comparison, like for reconstruction of the signals over different variety of graphs. And here different colors represent different level of noise. And this orange curve represents the optimal performance, and it's all comparable to the static case. So this indicated that actually the dynamic sampling can really offer a stable alternative for reconstructing the initial signal. And next, I want to talk briefly about application of real image. So here we have a image, like they are evolving over time, got blurring. So this can be modeled as a heat diffusion process. Then we apply our dynamic sampling. We do a little sampling on each time instance, and together with space-time samples, we want to do reconstruction. So you can see that in regime 2 and regime 3, we are really doing a great job, and we compare this SNR for different regimes. So you can see that in the static setting, we only get 21, but in regime 2 and regime 3, we can get much higher SNR. So the reconstruction are really good. So let me see. Yeah, I don't have much time left. So maybe, yeah. So here I want to maybe briefly mention about some work I did in the system identification problem in dynamic sampling. I think this is a very interesting problem to consider. So here we change the problem setting. So what if A is unknown? And then this completely changed the problem because now it's a nonlinear inverse problem. So we asked, can we recover both F and A? And F here still we don't have the dynamical assumption. So F is just signal in Cn, for example, from the space-time samples. So it looks very challenging, but the answer is surprisingly yes for some spatial instance. For example, if A is a convolution operator, so this is really like a super resolution problem. Like if we show that if A is like low pass filter, like Gaussian function, and yeah, so we can use dynamic sampling techniques to do the reconstruction. Actually, this work is done by Ajubi and Crystal back to 2014, where they proposed a Preliminary method to tackle this problem. Later, I realized that, yeah, so the essential structure is a Hankel matrix that can compute from the Fourier transform of this data. So in signal processing, other people actually propose the matrix pencil method and Ispira method as stabilized variants of this Preliminary method. And the people also use the causal denoising plus extra spatial samples to achieve stable recovery. So later I generalized results to the infinite dimension case, and more recently, yeah. So I take a close look of this system identification problems, dynamic sampling, and also make a careful comparison with other problems considered in control theory and also the structural signal recovery problem. Actually, people in control theory, they consider a time invariant linear dynamic system of this form. So this xt, so of course this is a simplified system. So xt is input and yt is output. So they are interested in like recovering this system matrix ABC from the pairs of xt and yt. It turns out that this problem is pretty much ill-posed. One cannot expect exact reconstruction. And what we can do at the most is to reconstruct this system matrix, this matrix here, up to a similar transform. And the people, you typically shift the focus to learn other parameters in the system, like some Markovan parameters that completely determine the behavior of X and YT. And recently there's some like work on like want to do the exact reconstruction, but there are results showing that they, we have to put a very restrictive condition on this simple linear dynamic system, like the A. And so they consider this simple linear dynamic system, but they show this A has to be very restrictive to achieve the exact recovery. And they also make connections to structure singular recovery problem. Yeah, so here I think this is this back to Peter and Planka in 2013, that they gave an abstract formulation to many singular processing problems considered in the field, such as blended deconvolution, recovery of signals with finite rate of innovations. And here we have actually some operator A, and it could be a shift operator, and it could be modulation operator depending on the applications. So we have a signal B here can be represented as a sparse representation of the eigenvectors. So you are given the data samples F, A, T, B. So you can see here, now it's a dynamic system. So you have to sample the dynamic system. You want to recover both the coefficient and the VGA from the data. And so a key assumption in their result, like A has to be known, and the eigenvalues are assumed to have geometric multiplicity 1. As long as you can recover the eigenvalues, you can identify this VGA. So that's the key of the recovery. So so motivated by this previous work, recently with my student, that we do generalization of the system identification problem to a fine system of this form. So why we are like interested in this problem, because this kind of simple system can include random walks, diffusion process, and a lot of other systems used in applications. And we consider the deterministic sampling regime, so we have partial observations. And goal is not to the exact recovery of A, but their eigenvalues. Because sometimes the eigenvalues tell us very useful information about the dynamic system, such as stability, and also the structure information of the graph. And this collection is studied extensively in the field of spectral graph theory. So we actually expand the previous algorithm to this more generalized setting, and we do the Preliminary method, and we do the recovery of eigenvalues. Especially, we treat it as a nonlinear inverse problem and characterizing the relationship between this omega 0, the sampling locations, with the recoverable eigenvalues for arbitrary matrix A without any diagonalization assumption. And we also provide like reconstruction algorithm, generalize the Prony and the matrix pencil in spirit before, and applicable to the case when this omega 0 is bigger than 1. And here I want to mention some relevant work by Bennett and Hazanasat, also published this year. So they consider this problem in the faceless, like when the samples lose a face, and they use the approximate Prony method to do the recovery of the eigenvalues, so which is very interesting work. So you can take a look there. Yeah, I don't have much time, so here I want to maybe show some like maybe 1 minute to show some examples. We test this algorithm a lot of systems. When the observations are exact, the algorithm work really well for all the methods like Prony, pencil, matrix pencil, and spirit method all work very well. And a challenge is how to determine the rank of the Hankel matrix. And we use the spectrum quotient matrix and look at the peak to pick the rank. And so it matched very well. And also, we want to test also the performance of this algorithm over the real data set. So this is actually example. So we take a human work motion data from the current Maine University. So this can be modeled as a linear dynamic system, which we use the dynamic model decomposition algorithm to get the operator A. And then we test our algorithm. Then we find out that maybe in this real data setting, this matrix pencil, SVD, and spirit perform much better than Prony. So that's kind of our motivation, trying to generalize the Prony method to the matrix pencil and spirit method. So this, I didn't have time to, so thank you for your attention. I'm happy to answer any questions.
Thank you very much. Questions? So if you have a question, then just go ahead and ask it, because I won't be able to see your raised hand.
Yeah. Thank you all. Thank you all for sticking to the,
All right. Well, if there aren't any questions.